All right, today we are diving deep into a mystery, a real puzzle that's hiding right at the very heart of science itself. It's a secret that kind of makes you question how we even decide what's real and what's not.
And it all starts with this one single number, 36%. Just let that sink in for a second. What on earth could a number that low mean in the world of science?
Well, here it is. When a huge project went back and tried to repeat 100 different published psychology studies, only 36 of them worked the second time. That is a shocking number, and it's the central clue in a mystery that scientists are now calling the reproducibility crisis.
So let's put on our detective hats, shall we? We are going to follow the clues to figure out why so much of the science we read about might be built on, well, kind of shaky ground. Think of this as a scientific whodunit, and believe me, we have some very interesting suspects lined up.
Okay, our first suspect is something you might have heard of, but it is way sneakier than it sounds: the p-value. This little number is basically the gatekeeper of science. It decides what discoveries get published and what research just gets forgotten.
So what the heck is it? A p-value tells you the odds of seeing your results if your big idea was actually wrong, if there was no real effect. And for decades, the rule has been that if those odds are 5% or less, a p-value of 0.05, then bingo, your result is statistically significant. It's a totally arbitrary line in the sand, but crossing that line, well, it's everything.
And that's really the key here. Getting your work into a big-name journal, landing research grants, even getting tenure, so much of a scientist's career hinges on getting that p-value under 0.05. And that intense pressure creates this huge incentive to find significance no matter what.
This pressure leads to a sneaky practice called p-hacking. Now, it's not always, mustache-twirling evil. It's more about fudging things in the gray areas. Maybe a researcher collects just a little more data, or drops a few outliers that look weird. Or they try analyzing the data in 10 different ways until, aha, that p-value finally drops below the magic 0.05 number.
And right here, this is the smoking gun. For real. When researchers looked at thousands of p-values from published papers, this is what they found. You'd expect a nice, smooth curve, right? But instead, look at that. There is a massive, totally unnatural pileup of results just under 0.05, and then a mysterious cliff right after it. This is the statistical fingerprint of researchers nudging their results across that finish line.
But wait, the plot thickens. P-hacking isn't our only bad guy in this story. Our next clue uncovers something truly bizarre, a really counterintuitive twist called the power paradox. And this one is all about how big a study is.
Now, you'd probably think that if a small study finds a big, significant result, that's extra impressive, right? Nope. It turns out that's totally wrong. Smaller studies, what we call underpowered studies, are not only more likely to miss a real effect, but get this, the significant effects they do find are actually more likely to be false. It's a complete mind-bending paradox.
Okay, to get our heads around this, let's try an analogy. I want you to think of a scientific study just like it's a medical test, like a test for a disease.
So, a study's power is its ability to correctly spot a real effect. That's a true positive. That p-value of 0.05 we talked about, that's the false positive rate. A significant result is basically like the test coming back positive. And we all know, a positive test isn't always right, is it?
Just look at this graph. See that green line? That represents a low-powered study, a small one. The chance that its significant finding is actually just a fluke, a false positive, is way, way higher than in a high-powered study, which you see there in blue. Bottom line, a flashy result from a small study is just less trustworthy.
Okay, so we've got two major suspects, these tricky p-values and these underpowered studies. But in any good mystery, you have to ask, what's the motive? Why are these things so common? Well, the answer is all about the intense, high-stakes culture of modern science.
The whole system, right, is built to reward flashy, new, exciting results. Getting published in a prestigious journal, getting more citations, and for a lot of people, just keeping their job and getting tenure. It all depends on churning out these significant findings. Careful, slow, meticulous science that ends up with a nothing to see here result, it just doesn't get you the same career points.
So what's the verdict in our whodunit? Well, here's the twist. It's not one bad person. The culprit is the system itself. The game is rigged to incentivize these bad habits. The solution isn't about blaming individual scientists, it's about fixing the rules of the game. And that starts with finding the right balance in how we design our studies in the first place.
You know, when it comes to how many people you include in a study, it's a real tightrope walk. If your study's too small, it's basically unscientific. You're just wasting everyone's time on an experiment that can't give you a reliable answer. But if your study's too big, that's also a problem. It's wasteful and it can be unethical, exposing more people than you need to potential risks.
And this graph shows it perfectly. It's the Goldilocks principle in action. Area A is too small. You're not getting enough bang for your buck. Areas C and D are too big. You're just getting diminishing returns. The sweet spot, the goal for all good science, is right there in Area B, the Goldilocks zone. Not too big, not too small, just right.
And that brings us to the final big question, doesn't it? We found the suspects, we figured out the motive, we know the whole system is the problem, so the real mystery we're left with is, how do we change the rules of the game? How do we build a new system that rewards scientists not for just finding significance, but for actually finding the truth? Now that is the real challenge.